Okay, well, as Phil said, I used to be a football player, and so football players need a little bit of cheering to get them going. So I think you all know how this works. I'll yell something out, you yell it back at me, and this will get the whole program started. Okay? So everybody, give me an I.
I.
Okay, louder next time. Okay? Give me an M.
M.
Give me a P.
P.
Give me an A.
A.
Give me a C.
C.
Give me a T.
T.
What do you get?
Impact.
Whenever I show this video, I may think twice about it, because when people see the Twin Towers there, of course, it brings up some pretty bad memories for us. But it does sort of give you this idea that even though human beings can be very destructive to one another, the destructive power of an asteroid impact could be dramatic, it could be catastrophic to the world. It could wipe out about 1 billion people just in one particular impact. But those movie clips that you saw there actually come from the movie Deep Impact by Steven Spielberg. And I was actually a consultant on that movie. And the astronomers who were consultants on that movie are very happy with it, because it turns out to be very scientifically accurate. Right? Armageddon, the movie that came out at roughly the same time as Deep Impact, wasn't nearly so scientifically accurate, but I have to admit it was a lot more interesting to see Bruce Willis blowing up an asteroid than little kids riding around on their bicycles. So Deep Impact was a nice movie, I still thought. And I looked online and figured out that Steven Spielberg probably made about $10 million on that movie. It was a big blockbuster kind of a movie, if you remember when it came out. Now, like I said, I was a consultant, and Steven Spielberg sent up one of his writers to talk to me. I was working at Kitt Peak, Arizona at that time. And that writer came up with me. He spent 5 hours picking my brain, and I told him everything I knew about finding asteroids. And for all my time and energy, I got $100. So, if you have kids or grandkids, or you're considering a change in your own career path, and you think that this sounds really exciting what I'm telling you about, you may want to think back to this particular slide when you decide to do something.
Which one's it? Should have got to director school after you got cut.
Is that why he has that smile on his face?
I'm sure he's smiling all the time. So let's start talking about the science now. This is the solar system as you may have seen it in school books when you were in primary or high school. And it's kind of like what we think about as a traditional solar system. But the thing about this slide is that there's almost nothing right. There's almost nothing correct in the whole slide. The colors are all wrong, the distances are all wrong, the scales of all the planets are all wrong, and it's got Pluto on it, which we all know is not a planet. So there's almost nothing right on this slide. So let's try and give you a little bit better impression of what the solar system actually is. And this here tries to give you the idea of the relative scales and the relative colors of these different objects. And I apologize, in the back here, you probably can't see some of these things down here. But Jupiter, if Jupiter was this big, okay, Jupiter and Saturn are really the two biggest objects in the solar system. Jupiter dominates the entire mass of the solar system. The Earth is quite small. It's something like, if Jupiter is the size of a basketball, the Earth would be something the size of a large marble. Right? And then other planets like Mars would be something like a small marble, and something like Pluto might be the size of a pea. So there's this huge disparity in the sizes of the planets. Even more impressive is the scale of the solar system. And to give you an idea of the scale of the solar system, of course I have to revert back to a football analogy. And I'm going to try and show you the solar system on a football field. So let's say we take the sun, which is something like 1 million miles in diameter. Okay, I mean, it boggles the imagination to think of 1 million miles, right? But try and imagine 1 million miles shrunk down to the size of a basketball and place it on the goal line. Notice also this is an American football field. I played football in Canada, so it's a little different for me. We have a 110-yard field, so our center line is 55, and so it's very confusing. Anyhow, so the sun is the size of a basketball on the goal line. And then if we think about Mercury, Mercury would be the size of a pinhead. Okay, not the size of the whole pin, but just this part of the pin is the size of Mercury. And it would be on the 11-yard line. Mercury, Venus, and the Earth are both about the size of a pea, and they would be on the 20 and 28-yard line respectively. Okay, so just think about that. How small a pea is, how big a basketball is, and they're separated by 30 yards, and that's roughly the scale of our solar system when we look at the sun. And it'll come up a little bit later, so I want to show this moon on the same scale. The moon on the same scale is 3 inches from the Earth. Okay? So 30 yards between the Earth and the sun, 3 inches between the Earth and the moon on the same scale. And the moon will be the size, not of a grape, but of the grape seed. Okay? So it's this grape seed going around this thing the size of a pea. Mars would be, again, about the size of a pinhead near the center line of the football field. Okay? Now that's the scale of what we call the inner solar system. Mars inwards we call the inner solar system. To get the rest of the solar system on a football field, well, you can't. So to get more, to use this analogy further, I have to add another 10 football fields. Okay, so we have 11 football fields here laid end to end. And you can add on the rest of the planets, Jupiter and Saturn, these are the 2 giant planets. They're 150 and 270 yards away from the basketball that represents the sun. Uranus and Neptune are both about the size of maybe garbanzo beans, maybe a little bit bigger than peas, maybe garbanzo beans. A third of a mile and half a mile away from the basketball. And finally, tiny little Pluto, which for this particular situation I'll consider a planet, is again the size of a pinhead, 2/3 of a mile away from the basketball. And I think it's really incredible to think that this little pinhead, right, is held gravitationally bound to this thing the size of a basketball 2/3 of a mile away. And I think it's just incredible to think how tenuous that graph must be, and yet it's been there for over 4.5 billion years going around the sun very regularly. Now, so that gives you the scale of the solar system and where the planets are all located. But let's talk about things like asteroids and comets. Asteroids and comets, most of the asteroids in the solar system reside in something known as the asteroid belt. The asteroid belt, well, okay, let me tell you what this is first. This here represents the sun. This represents Mercury, Venus, Earth, Mars, and if you're lucky, somewhere up here, in the corner somewhere, you'll see this red, white dot going by that represents Jupiter at some point. So this area here between Mars and Jupiter is the asteroid belt. All these little blue dots represent asteroids, and they're all going around the sun in the same kind of a direction. And there's about 1 million asteroids out there larger than 1 mile in diameter. Now most of them are perfectly safe out there. They've been there for 4.5 billion years. They're not going anywhere. But every once in a while, one of them kind of gets off course and it comes into the inner solar system. And these little yellow dots here represent something known as the Near-Earth Object Zone, or the NEO zone. Okay? Some of you may remember Neo from the Matrix movies. I like him a lot because he's not only Hawaiian, but he's also Canadian. So really great to get the connection between me and Keanu Reeves. So this region here, any asteroid that comes within this circle, which is a circle 30% larger than the radius of the Earth's orbit, anything that comes inside that yellow circle is called a near-Earth object and may someday hit the Earth. These are the asteroids that we're most worried about. So I've been talking about asteroids and comets a little bit, I think I mentioned, but I haven't actually told you what they are yet. Okay, so this is an actual image of an asteroid taken by a spacecraft that went to visit it. All asteroids look like potatoes. Okay? So whenever you think about an asteroid, think of something that looks like a potato, but it's mostly made out of rock. And this particular one is rotating because the spacecraft is actually going around the asteroid, and so it took pictures in different orientations and they stitched it together into this movie. And you can see the surface of the asteroid is covered with these pits, which are themselves pits that are caused by impacts by other asteroids on this asteroid. So all the asteroids are sort of bumping and grinding against one another, beating each other up and creating all these pockmarked scars on them. Now comets, on the other hand, are something a little bit different. This is kind of like what you might think about a classical comet. It's just a clip that keeps repeating. There's a very bright, very large, what we call coma here. The comet itself is something maybe only about 1 mile in diameter, the very center of this particular coma here. The coma could be something about 1 million miles in diameter, but it's a very, very tenuous gas. Very, very tenuous. There's almost nothing there at all. And then the coma sort of gets blown backwards to something that we call the tail. You can see the tail moving in this particular image here. Comets have this particular look because they're made up of ices, typically water ice. And the water ice, when the comet gets close to the sun, the water ice basically melts or sublimates off of the surface of the comet and then gets blown behind the comet, creating this beautiful tail that we see. So comets are kind of icy, and asteroids are kind of rocky. And it used to be that people thought that that was the exact distinction. All asteroids are just rock, all comets were just ice. But in the last, say, 20 or 30 years, we've learned that the distinction isn't really clear. That asteroids are more like icy dirt balls, and comets are more like dirty ice balls. Okay? And there's a whole spectrum between the two. You know, there can be some things that are just pure rock, and there can be some things that are pure ice, but there's really a whole spectrum, and where they fall just depends upon the relative fraction of rock and ice. But of course, a long time ago, people didn't know the difference between asteroids and comets, so they thought they were really different things. Now we actually know that they're actually quite similar. There's also something called meteors, which you probably know certainly as shooting stars. Probably most of you have seen a shooting star. Shooting stars are not really stars that are falling, but in fact they're chunks off of asteroids or comets that have entered our atmosphere. Typical size of shooting stars, something that you might see when you're in your backyard, lying out maybe in a forest or something like this, looking at the sky, is the size of a pea. And the reason it looks so bright is because it's entered the atmosphere at about 20 miles per second. That's about 20 times faster than the fastest bullet coming out of a rifle. Right? So you get this, something the size of a pea entering the atmosphere 60 miles above your head at 20 miles per second, and it literally burns the surface. What you're seeing when you see a shooting star is the burning surface of this tiny pea-like piece of rock that's going through our atmosphere. And it burns up 60 miles above our head. What you're seeing here is a very large shooting star. This thing was the size of about a Volkswagen when it came into the atmosphere. It broke up, you see all the little chunks that fall behind it. It broke up and it was captured on film because it fell on the eastern seaboard on Friday night when everybody was out in the fall, when everybody was out watching their kids play football. And so everybody's got their video cameras looking at their sons on the football field, and then the sky lights up. There was actually shadows cast by this thing on the ground. And if everybody looks up, and then everybody got all sorts of video of this thing. So we have hundreds of videos of this particular shooting star. So this thing was the size of a Volkswagen when it entered the atmosphere. It broke up and burned up in the atmosphere, so that the only thing that made it to the surface of the Earth was some pieces about the size of your fist, maybe, the size of a baseball or something like that. And at the very end of this video, you probably saw the track that the meteor took across the surface of the Earth, and eventually one of those chunks of rock slammed into I believe it was the trunk of a car just outside of New York City, and it did quite a bit of damage to the car, as you can see right here. So, my point in showing you all those things is that all these things used to be thought of as quite different. Asteroids looked like tiny points of light in a telescope. Comets looked like these fuzzy tails. They were fuzzy and they had tails. And shooting stars moved very, very fast across the sky. And so astronomers, up until a few hundred years ago, thought that all these things were actually very different. But now we know that they're all the same thing. They're all just small bodies in our own solar system, exhibiting different properties. So up close and personal, we can look at an asteroid. This is a very large asteroid known as Ida. I personally hate going to talks where they talk about these things and they say something's large or small and you never get an idea of scale. So in all my slides, I'm going to try and give you an idea of scale. And so I'm going to compare Ida to Oahu. So you can see that asteroids can be quite large. This asteroid is literally as large as Oahu. Now fortunately, we know that there's no asteroid this large that can hit the Earth. We were absolutely positive of that. The largest asteroid we know of that can hit the Earth is only about 5 or 6 miles in diameter. But still, a 5 or 6 mile in diameter asteroid would wipe out all life on our planet. It would wipe out all of civilization. So how do we find asteroids? It's a pretty simple technique, actually. What we do is we go to one portion of the sky and we take an image. So we might go, yes, we observe all night long, of course. So at midnight, we may go, we take an image of the sky. This thing that you see here is a galaxy, a very distant galaxy. These other fuzzy patches you see here, they're all galaxies, all these fuzzy things. Some of the things that look more pinpoint-like this and this, this and this are stars. Okay, and we come back to exactly the same location, maybe half an hour later, and we take another image of exactly the same location. And again, about a half hour later. So now we have 3 virtually identical images of the same portion of the sky, and we superposition them on top of one another. Of course, we do this all on the computer. It used to be 20 years ago, they actually did this by eye with photographs or with computer screens when they got a little bit more advanced. Nowadays, we don't do that. We write computer programs to do all of this for us, and so I'm just sort of exhibiting what the computer program is doing. And then once the images are superpositioned, we blink them. We go very rapidly between the three pictures. And anything that's stationary, like a galaxy or a star, doesn't move at all. Right? So all the stars and galaxies, they're all fixed in location. They don't move relative to one another. But the asteroids, you can see one here, you can see one down here. The asteroids are moving in our solar system, and therefore they're moving relative to the Earth and relative to the stars and the galaxies. So this is how we find the asteroids. The computer program actually goes in, identifies things that are moving in the images, and then spits out a message to us saying, hey, I found an asteroid. So what is the risk of one of these asteroids actually hitting the Earth? Well, there's actually this website out there made by one of my friends, the husband of one of my colleagues here at the Institute for Astronomy. He made this website called Ask 500 People. And you can literally go onto this website and you can ask any question you want of as many, in this particular case, 100 people. But they want to get it up to 500 people. So you can go and ask the question. Now, unfortunately, I did not ask this question. Somebody else did. But I thought it was very interesting. How likely is it that the Earth gets hit by an asteroid in the next 50 years? And you can see these little pinpoints on the map showing where people responded from around the world. So around the world, 29% of people thought that it was very unlikely that the Earth is going to get hit in the next 50 years, whereas 12% thought that it was very likely. In the United States, the results were very similar. Maybe 14% thought it was very likely in the United States specifically. But other than that, the results are pretty similar to what they were around the world. So I want to ask you, in your head right now, given what I've already told you, okay, what do you think is the probability that we're going to get hit by an asteroid in the next 50 years? So I won't keep you in suspense. The answer is 100%. Okay? Right? We always get hit by asteroids. I just told you that small bodies, the shooting stars, are pieces of asteroids and comets, and shooting stars are hitting the Earth all the time. The mass of the Earth increases by tens of tons per day because it's running into the asteroids and comets. And if you're smart enough, you can actually take the dust in your living room. You can actually put it under a microscope and you can look at it. If you sift through enough of it, you'll find little pieces which are actually the burnt remnants of the surfaces of these shooting stars that came down. So you're actually vacuuming this stuff up. Of course, the Earth weighs much more than tens of tons, so it doesn't really affect the mass of the Earth that much. But they get hit. We get hit all the time. The real question that this should have been asked on this website is, how likely is it we're going to get hit by an asteroid that kills 1 billion people? Okay? And that's a more interesting question than whether or not we're going to get hit in the next 50 years. So let me sort of walk you through the solar system a little bit to give you an idea of what the risk might actually be like. This is an image of the sun, where the sun itself is is hidden behind this what we call an occulting disk. And the sun size is represented by this white circle right here. These things you see out here is basically the atmosphere of the sun. To give you an idea of scale again, so if this represents the sun, the Earth is this little blue dot. Maybe some of you can see if you're in the front row, but if you're in the back row, you probably can't see it. And there's this tiny little blue dot at the bottom of this arrow that represents the Earth. So the Earth is tiny. Now I'm going to run this video, but I want you to sort of start off looking down to this area right here. Let's run it. Boom. See that? So there were 2 comets that came in from the bottom here at the same time and hit the sun. And now it's just running over and over and over again. But the point is that the sun gets hit by comets on a daily basis. Every day, the sun gets hit. So remember, the sun is represented by this basketball on the goal line. Jupiter is the second largest object in our solar system, right? We learned that in the very beginning. Here's a beautiful movie of Jupiter rotating. And back in 1994, some of you may remember this comet called Shoemaker-Levy 9 that went by Jupiter. And it made one pass by Jupiter, kind of went by kind of like that. And in the process of going by it, it got affected by something we call tidal gravitational breakup. So let's take a look at what happens to an asteroid when it goes very close to a planet. Let's say you get something that looks like an asteroid. Now, of course, this is not to scale, right? At this point, I couldn't do this to scale. When you have an asteroid that's kind of like this, maybe it's 1 mile across or something like this. Well, this edge of the asteroid here that's closest to the planet is going to feel a very strong gravitational effect. But this edge here is 1 mile further away from the planet, and so the gravity is less strong. So it's going to feel less of a gravitational effect. So what's actually happening here is here you've got something, imagine if you've got sort of a really strong kid and a really weak kid pulling on, a stick, right? What's going to happen? The stick's going to shatter, right? It's going to rip apart. So that's what's going to happen. There's actually this force that's trying to rip the asteroid apart because of this differential force of gravity across the distance of the asteroid. This actually happened to this comet. Comet Shoemaker-Levy 9 went by Jupiter. It was about a mile in diameter, and it literally got ripped apart by the force of Jupiter's gravity. And in the process of ripping apart, it created something like 16 different pieces that were all now separate chunks that were orbiting around, in this case, Jupiter. And it just so happened that the way that the comet went by Jupiter, it modified its orbit just enough that actually when it started looping back, it was going to hit Jupiter. And this kind of a Jupiter, this is a simulation, animation of what it might have looked like from one of the chunks slamming into Jupiter. And after a few days of impacts of all these 16 different chunks, you can see these impact stars on the planet. Right? So each one of these black marks here is an impact star on the planet Jupiter. Now I showed you what the relative size was between Jupiter and the Earth earlier, but just to remind you, the Earth is about this size. Okay? So the impact stars on the surface of Jupiter are as big as the planet Earth. Okay? And this is by an impact of chunks of rock that are smaller than a mile in diameter. So what is the Earth impact? Because we just saw that the Sun gets hit all the time, right? That Jupiter gets hit all the time. So what's the risk that the Earth gets hit? This is an artist rendition. It's kind of funny to astronomers. Astronomers would laugh at these things because this asteroid is huge, right? I mean, there's nothing like this is ever going to hit the Earth anytime in the next 5 billion years. But back when the Earth was forming, 4.5 billion years ago, asteroids this size did impact. So the Earth looks something like this, right? It's this beautiful blue ball, a little bit of land, about a quarter or a third of it is land covered. But it looks, you know, if you've gone around and you haven't really thought about it very much, it might look like the Earth is very pristine, like there's no craters, no evidence of any impacts at all. But if we look at the moon is covered with these circular scars. And you can see each one of these tiny little circular scars here is a crater caused by the impact of an asteroid or comet sometime during the last 4.5 billion years. To give you a scale, I've shown the Hawaiian Islands to scale here. Okay? So you can see that some of these craters, the even small craters here you can see, are the size of individual islands in the Hawaiian Island chain. And you can also see that some of the big craters here are the size of the entire Hawaiian Island chain. Right? These are craters here where an asteroid that was large enough it actually punched through the crust of the moon, and lava from the inside flowed up to the surface and filled the basin itself. So the moon is covered in craters. It's saturated with craters, in fact. So the moon and the Earth look something like this to scale now. This is the actual Earth and moon to scale. Gives you an idea of how much space there is between them. But remember from my solar system on a football field that the Earth and the moon are really separated by just 3 inches on the entire football field of the solar system, right? So the Earth and the moon are really, really right next to each other. So why then does the moon look like it's covered with craters and the Earth not? Well, I think you probably know it's because 3/4 of the Earth's surface is covered with water, and so an impact into water is not going to leave much of a crater. Impact onto land on the surface of the Earth is going to be wiped out by tectonic processes, by the crustal plates moving around, by erosion, by human beings. There's in Germany there's a city that's built in the middle of this impact crater. And they didn't know about it for a long time because there have been so many buildings and roads built across it that they just didn't know about it. But you know, human beings are even wiping out the effect of all these craters. So if it weren't for the fact that we have water and plate tectonics on the surface of the Earth would look just like the moon. We're right next door to each other. There's no reason that the Earth would look any different than the moon. So our little planet Earth, so beautiful, where we all live on this tiny little thin surface, right? Actually looks like this to an asteroid. The Earth is a target, okay? And there are, as I've just said, asteroids with our name on it out there. There's been, so you probably have never seen an asteroid crater on the surface of the Earth, but in fact there are many of them, and people look for them and they're being identified all the time. This shows a map of where known asteroid impact craters are on the surface of the Earth. If you look at it closely, you might think that, wow, the asteroids really hate North America and Australia and Northern Europe, and they seem to be pro-communist and like pro-environment, and they're not destroying the Amazon at all. But in fact, this is all just an accident of politics and also climate, right? Because in Amazon, anything that hits there and wipes out a bunch of land quickly gets grown over, right? So if there's an asteroid impact that wipes out hundreds of square miles, within 1,000 years, 2,000 years, it's all grown over again with plants. And in Siberia, it's a great place to find craters because it's just a whole bunch of rock that's just barren, like northern Canada, where we found lots of rock, lots of craters. But it's always been difficult to get into Siberia to actually find these things because of politics. So Australia, Northern Europe, and North America are great places to find asteroid impact craters, and that's where you found them. Probably the most famous to give you an idea what these craters actually look like, this is a double impact crater. It turns out this is only something that was discovered within the past 10 or 15 years. While my career in astronomy has been going on, we've learned that a lot of asteroids are actually double asteroids. They sort of rotate around one another. And so this is probably a double impact structure due to two asteroids that were rotating around each other, slamming into Earth at exactly the same time. It's not two independent asteroids that just happen to hit the same place on the Earth. That would be extremely unlikely. Two bullseyes, playing darts in a row. But they were almost the same size asteroid. This asteroid was a little bit bigger because it left this internal ring structure here. And this is a very common phenomena when you've got large asteroids striking the Earth. They create not just a crater, but they create a ring inside the crater. Right? So this is how you can tell that it was a really big impact. But again, I like to give you scale. So this is a Wahoo. And this is, remember, this is not the size of the asteroid. This is the size of the crater. And if the crater's this big, it means it wiped out something the size of a state Lincoln. Okay? That asteroid impact took place about 300 million years ago. This asteroid impact took place about 200 million years ago. It's in, both of these actually are in Canada, both these craters, Manicouagan crater. And what's actually happened here is it looks like an inverse crater because there's so much erosion taking place here. This impact took place 200 million years ago, and Oahu is that big. Okay, so this is a much bigger crater even than the island of Oahu. So 300 million years ago, 200 million years ago sounds like a long time. This asteroid was created this crater was created only 50,000 years ago. It's in northern Arizona. It's called Barringer Crater. It was created by the impact of an asteroid just 50 yards in diameter. So something not much bigger than the size of this building, perhaps, struck the Earth at 20 miles per second, created a crater 3/4 of a mile across. Now, I went to see this for the first time about 15 years ago. And I thought I'd be kind of jaded because I'm an astronomer, I know what these things look like, right? But I went to the visitor center, which is somewhere over here, and I walked up to the lip of the crater, and I looked over it, and I realized, wow, this is incredible. It's a crater 3/4 of a mile in diameter caused by the impact of an asteroid 50 yards in diameter. And then you begin to realize that when this thing hit, it probably wiped out everything in northern Arizona at the time. And this kind of thing can happen at essentially any time. So, this is, again, all the asteroid impact locations around the world, but the most famous one is probably this one right here on the northern coast of Yucatan Peninsula of Mexico. The center of the crater is very near a small town called Chicxulub, and so this impact crater is known as the Chicxulub crater. It was caused by the impact of an asteroid about 6 miles in diameter, 65 million years ago. Now, 65 million years ago, some of you may recognize, is also about the time when the dinosaurs went extinct. And we now know with absolute certainty that an asteroid killed the dinosaurs. There's just no doubt about it. Up until about 30 years ago, people used to debate, whether it was due to volcanism, or if it was due to an asteroid impact, or due to disease, or whatever. But now we have virtually incontrovertible proof that the dinosaurs were killed by an asteroid. Now, I like to think that human beings are smarter than dinosaurs. Dinosaurs, were very large animals, but they had brains the size of peas, right, or walnuts. Now, we have large brains, small bodies, very high intelligence, we like to think. So I like to think we can do something about stopping the asteroids from hitting the Earth. This is a computer simulation of what it might have looked like, what the surface of the Earth might have reacted like when the asteroid impact took place 65 million years ago. To me, it looks like the surface of a glass of milk when the last drop out of the carton falls into it. You can see, let me wait till it gets started again, but you can see the flat surface gets disturbed in the very beginning. You get large crater forms, the Earth then rebounds, right, creating this mountain that then collapses, and the mountain then collapses. When it collapses, it forms this internal ring. Remember I told you about the internal and the external rings. So this is a very large impact crater. The really amazing thing about this is the scale that we're talking about. That is Mauna Loa to scale. And I'm not talking just this part above the water. This is the part from the ocean floor. So from the ocean floor to the top of Mauna Loa, we all know Mauna Loa is the tallest mountain in the world when measured from the base of the ocean floor. And this is the Mauna Loa to the same scale as this particular impact. So this mountain here was a couple times the size of Mauna Loa. And it formed in 5 minutes. A mountain that's twice the size of Mauna Loa formed in 5 minutes, and then it collapsed back down in 5 minutes. The temperature, the surface temperature on the entire surface of the Earth was the was the temperature of an oven, 450 degrees Fahrenheit. The entire surface of the Earth was at 450 degrees Fahrenheit for hours after this impact. So virtually anything that was on the surface of the planet got incinerated. Okay, still, 65 million years ago sounds like a long time to human beings. So let's move a little bit closer in time. This is a place known as Tunguska. This picture was taken in the early 20th century. And it's known as the Tunguska Impact Site. An asteroid, so this asteroid hit 100 years ago this year, 1908. Okay. And this asteroid was only maybe something like 20 yards in diameter when it hit the atmosphere. It did not even make it to the surface of the Earth. The Earth's atmosphere acts like a protective coating around the Earth, and it literally blocks the smallest asteroids from hitting the surface. An asteroid has to be larger than about 50 yards in diameter in order to actually make it to the surface and create a crater. Anything smaller than about 50 yards in diameter gets broken up by compression and shock waves that occur in the atmosphere. So what you're seeing here, all these trees that got knocked down over an area of about 100 square miles. And these are trees maybe a foot in diameter. Okay? All these trees did not even get knocked down by the asteroid striking the Earth. They got knocked down by the blast wave that came as the asteroid just got destroyed itself in the atmosphere, and that blast wave hit the surface of the Earth. 100 square miles, foot diameter trees all knocked down. If we had Tunguska versus Oahu, it would look something like this. It would wipe out all of Oahu if the asteroid took place, the impact took place over central Oahu. The yellow region would have been burnt and blasted, so like actually trees would have burned down in this region here. And the red region would have been just blasted, so all trees would have been knocked down. My boss who works here, the director of the Institute for Astronomy, lives over here somewhere. He says, oh, you know, that's great because my house wouldn't get knocked down. So yeah, you can see that Tunguska, even Tunguska, an asteroid that didn't even make it to the surface of the Earth, could be very, very damaging to the surface. And if that asteroid had hit the Earth only 3 or 4 hours earlier, it would have hit London, England, killing millions and millions of people. So if asteroids are so scary and asteroids are so dangerous, and why isn't it that you don't hear about asteroids falling on churches all the time, or you walk down your hallway and finding a coworker underneath an asteroid? Well, it turns out that it's even though it's dangerous, it's also very complicated to figure out what the risks are. So let's figure out how we actually measure the risk as astronomers or scientists. We do a lot of simulations in astronomy because asteroid impacts don't happen often enough for us to be able to go out and measure it. And we wouldn't want them to happen, right? We wouldn't want asteroid impacts to happen every year because it would kill a lot of people. So instead, we have to sort of rely on our statistics and our imagination and extrapolation from theories and from our own experiments. So if we want to figure out how much damage an asteroid impact is going to cause on the surface of the Earth, we can do simulations. And they sound kind of silly because when we talk about an asteroid 1 mile in diameter striking at 20 miles per second, you can't simulate that. Right? You can't simulate that. So what we do is we take things the size of maybe marbles that are made out of things that's made out of material like an asteroid, and we shoot them at almost the speed of an asteroid, say 10 miles per second or 5 miles per second. And we shoot them at a chunk of material that represents the surface of the Earth. In this particular case, it's something like a piece of basalt or a piece of chalk or something like that. And so what's going to happen is this simulated asteroid is going to strike the chalk, and it's going to create a massive explosion. And if we let it go long enough, all this material that gets ejected here is going to fall down over here. And some of this material that gets ejected in a real asteroid impact, like the one that struck the Chicxulub 65 million years ago that wiped out the dinosaurs, that material went all the way around the Earth. Okay? So you can see this material here is just falling outside this region right here. And you can see after the dust clears away, you can actually see a crater in the very center here. So we can simulate what's going to happen with asteroid impacts in the laboratory, and then we can extrapolate from these little tiny experiments using mathematical theories to what would happen if you had a mile diameter asteroid striking at 20 miles per second. But that's just one part of the equation. So we know from those kind of simulations how much damage an asteroid will make when it hits the Earth. but we don't know the rate at which the asteroids strike the Earth, right? So we do more simulations to figure out the rate. So, once again, I have a football here, okay? And so, we simulate it. Let's try and do a simulation of what happens when an asteroid strikes the Earth. So we throw that asteroid at the surface of the Earth, and it creates a crater, okay? And then we can take more asteroids, and we can continue the simulation, right? Oops, wrong place. And we can continue the simulation, and we can keep doing the simulation and seeing what happens as different asteroids hit the surface of the Earth and create craters of different sizes, right? And if we run the simulation over for a long period of time, we get something that looks, I think you'll admit, even though it's a schematic cartoon, that it looks a lot like the surface of the moon. Right? It looks like it's saturated with craters. It looks very much like the way the moon looks. And we even simulate some things like when there's a very big crater comes in, a very big asteroid, it wipes out lots of other craters. Small little craters can happen inside of big craters. So by measuring how long it takes for a surface, a simulated surface, to begin to look like the surface of the moon, we can then measure how many impacts had to take place in order to create the surface of the moon. And in that way, we know the age of the surface of the moon, we know the way it looks, we can measure the number of craters, we figure out the impact rate. Okay? So there we have, now we have how much damage an asteroid causes when it strikes the Earth by doing these simulations in the laboratory, and we know the rate at which asteroids impact the Earth. So now we have to get into some pretty morbid calculations. Let's do the calculation first for the rate, the risk of you dying due to an airplane crash. Okay, I apologize, you're all going to go home and have nightmares after this talk now. But if you look at the number, if you want to calculate the risk of you dying in an airplane crash, you take the number of people in the U.S. who die in a plane crash every year and divide it by the number of people in the U.S. And actually, we've been, I think, aircraft crash-free since 9/11. It's pretty incredible. So that's fantastic. But on average, something on the order of about a few hundred people die per year in airplane crashes. There's about 300 million people in the United States. So that means that 1 in a million, there's about a 1 in a million chance of dying per year in an airplane crash. And if you live, say, 100 years, to make the math easy, it means there's a 1 in 10,000 chance of dying in an airplane crash in your lifetime. Very simple math. And this is wrong by a factor of a few, but it's just to make the math easy to give you the idea. So now we try and do the same risk calculation, but for asteroids. So we say the number of people who die in asteroid impacts around the world per year divided by the number of people in the world. And well, that's some number over 6 billion roughly. But we don't know how many people die in asteroid impacts because nobody's ever died from an asteroid impact. So it gets a little complicated. So again, we resort to these risk simulations. And we do these kind of simulations where we pretend an asteroid was to strike here. And we say, okay, well this asteroid would wipe out all this region right here, but there aren't a lot of people there, so it doesn't matter that much. And then there might be another asteroid impact over here, and you might say, well, there aren't a lot of people who live within that circle, so it doesn't really matter that much. But an impact right here would create a tsunami that would create a huge wave on the coast of Europe and on the eastern seaboard. And so it would wipe out a lot of people, because a lot of people live at very low elevation relative to sea level. And similarly, we do this many, many times in our simulations. We know what the population distribution is around the world. We actually figure out what the risk of each impact killing people is, and then we can sort of average it out, and we can figure out what the risk of people dying. So now we know all the different things, all the different parts of the equation tell us what the risk of people dying is per year. And it turns out that the risk of you personally dying due to an asteroid impact, okay, is about 1 in 20,000. So that's something comparable to the risk of you dying in an airplane crash, right? Now that's maybe not such an interesting calculation, because you think 1 in 20,000, you personally dying, maybe that's not so important, because what you're really concerned about is what kind of a risk is there that there's going to be some sort of major impact a century that might wipe out a country and just send the economy into a tailspin. And so the risk of a major impact occurring this century within our lifetimes and our children's lifetimes is about 1 in 1,000. So 1 in 1,000, I think, is pretty serious. So what if we find the big one? What if we find one that has a good chance of actually hitting the Earth? Well, to some extent, we kind of already have. Okay, we don't know that it's going to hit the Earth, but it has about a 1 in 20,000 chance of hitting the Earth. It's an asteroid known as Apophis, and it's on this. So you've already seen this kind of solar system diagram: Sun, Mercury, Venus, Earth's orbit, and Mars. So the Earth's orbit is in green. And the orbit of this asteroid Apophis is in red, and you can see that it crosses the Earth's orbit at 2 different points there. Now this isn't really fair, because anytime you project something onto 2 dimensions that's actually 3-dimensional, there's always going to be a crossing point. But in this particular case, you're just going to have to trust me that where it crosses here, it really, really comes very, very close. Okay? And this asteroid is extremely dangerous. It's about 400 yards across. If it was to strike the Earth, it would wipe out something the size of maybe the United States, Canada. On Friday, April the 13th, 2029, and I'm not joking, it's Friday, April the 13th, 2029, this asteroid is going to come extremely close to the Earth. A few years ago, there was about we thought there was about a 1 in 30 chance it was going to strike, but after we got more observations and more calculations, we realized in 2029 it's not going to hit. But in 2029, it's going to come very, very close. Its incoming path is going to be something like this, and then it's going to come very close to the Earth. The range of possible distances from the Earth, we're not exactly sure where it is, but we know that it's going to be somewhere in this kind of a range right here. It's going to come so close to the Earth that the Earth's gravity is going to cause the orbit to bend, and it's going to come out in this direction here. So now let's say that you're on the asteroid and you're looking sort of in this direction, right, towards the point where you're going to hit the Earth. And so from the asteroid, the region that you are going to pass through is kind of like this region right here. Okay? And it's kind of fuzzy because we're not really sure exactly where it's going to be, but we are sure that it's going to miss the Earth. Okay? This distance here is about 20,000 miles. The distance between the Earth and GPS satellites that we all use, right, to measure where we are, is about 24,000 miles. So this asteroid is going to come between GPS satellites and the Earth. It's going to be visible to the naked eye as a star about as bright as the stars in the Big Dipper if you're in Europe on Friday, April 13, 2029. And you look up at night, you're going to see this thing that looks like a star whipping across the sky. That's this asteroid Apophis. But the really scary thing about this asteroid, I haven't even told you yet, is that if it passes through this tiny little, what we call a keyhole, there's one tiny little region right here, and it's not to scale because it was too small to drop. But if the asteroid happens to pass through this keyhole, then it's going to hit the Earth on April the 13th, 2036. And the odds of it going through that little keyhole are about 1 in 20,000, 1 in 30,000, something like that. So small odds, right? But if it goes through that keyhole, then it's going to hit the Earth for sure in 2036. And if it hits the Earth in 2036, we know exactly, well, we know where it might hit. It's going to hit somewhere along this line. Okay? So, where's Hawaii? So this could be very bad for Hawaii. There's somebody here from the Pacific Tsunami Warning Center. So somebody's going to be working overtime on the 2036, I think. Don't sign up for that shit. So this is the impact. It's kind of incredible, right? To think that we can predict 30 years in advance what the path or what the possible locations are of this asteroid if it's going to strike the Earth. So what do we do if this thing is actually going to hit the Earth? What if we find the one that's going to hit the Earth? Well, lots of people actually spend a lot of their brain cells thinking about these things. My former boss, a guy named Tom Garrels at the University of Arizona, was a big guy in this field. He published this book called Hazards Due to Comets and Asteroids, where a lot of people got together to try and figure out what you do. And the biggest thing you want to do, the best thing you want to do is deflect the asteroid. You don't want to go blow it up Armageddon, Bruce Willis style, because then all you do is you create a bunch of buckshot that hits the Earth. Okay? You want to go and you actually want to deflect it from hitting the Earth. So let's talk about how you might do that, or what's it all about. So let's say we've got this little toy model of asteroid going to hit the Earth on Earth's circle on Apophis Avenue. Boom. And you do not want that kind of a collision to take place. Okay? What you really want to do is you want to go out there and you want to, at some point, you want to go and you want to get up close to the asteroid and you somehow want to deflect it. And you just want to slow it down a little bit. Speeding it up would work just as well, but you want to just slow it down just a little bit. If you slow it down just a little bit, boom, and this is good. So what we want to do is take this thing that is the target of the Earth, right? And we want to move it over. Okay? Now the thing is that if we don't deflect it enough, okay, then we're just targeting some other point on the Earth, right? So imagine that map I showed you on April 13th, 2036 of the path that the asteroid might actually hit on the surface of the Earth. Well, let's say we go try and deflect it, and we do it wrong, okay? And so now all of a sudden, rather than hitting Russia, it's now going to land on the United States. Okay? That's not a very good thing. Right? So when we go off and we deflect it, we got to be really sure that we push that whole thing off the surface of the Earth. Right? We want to do it very well. So how do we go about doing this? Well, the most obvious way to do it, probably occurs to you automatically, is explosive deflection. We launch some sort of a spacecraft that goes up there. To get enough bang for our buck, it's probably going to have to be nuclear. And we go up to the asteroid, we get the bomb very close to the asteroid. Like I said, we do not want to blow it up. So we just want to get close to the asteroid, and we want to detonate the bomb close but not on the asteroid. So we blow it up, and we move the asteroid. Now, most people think that it's the force of the explosion that's going to move the asteroid, but I'd just like to talk about a little physics here. What actually happens is that the explosion from the bomb will basically blow chunks of rock off of the surface of the asteroid on the side that's facing the explosion. These chunks of rock blow off in this direction, and we all know from our freshman physics classes that for every action there's an equal and opposite reaction. So the reaction of the asteroid to the rocks being blown off on this side is that the asteroid moves in that direction. Right? So this way we get the deflection of the asteroid. But this is not really a desirable way maybe to deflect an asteroid because it requires nuclear explosions. You've got one shot at it. If you don't do it right, if you don't detonate the right time and place, you basically can screw things up. Or if you don't have a big enough bang, all these things can happen. Also, we're not really even sure what most asteroids are formed of. We don't know if they're like rocks or like pillows. Okay, and you know, if you go bang a rock, the rock moves. If you go bang a pillow, the pillow absorbs your force. Right? So if an asteroid is more like a pillow, when we try and move it this way, we may not be very successful in actually moving it. There's a few other ideas for deflecting an asteroid. One of them might be considered solar deflection, where we might launch a bunch of mirrors. And then this is nice because you could launch many of them. So if one or two of them fail to go off the space, the launching pad, or fail to make it to the asteroid because of some other spacecraft failure, you can still got a few of them that actually end up at the asteroid. And then you focus the light from the sun onto the surface of the asteroid and burn off, or burn up the surface of the asteroid, and you knock stuff off the asteroid in that way, right? And so in the same way, when you knock the rocks off this way, the asteroid is going to blow off in this and get deflected in that direction. But maybe one of the most elegant ideas for deflecting an asteroid is something known as a gravitational tugboat. It's not exactly like a Star Wars tractor beam, but it's not so far off, actually. The idea is that you launch a spacecraft that's very massive. All you care about is getting a very massive spacecraft up there. And massive, by massive I mean something the size of a truck or something like that. And then you navigate the spacecraft to a place that's close to the asteroid, but maybe just ahead of it in its orbit or just behind it in its orbit. And you have these rockets. You can see the rockets do not come out the back. The rockets, the rockets are blowing off to the side. And you navigate the spacecraft so it gets close to the asteroid, and then this tiny little tug from this tiny little mass here actually exerts a little bit of force on the asteroid. And you can steer the asteroid very, very slowly away from any impact site. So this is a really nice way of doing it. And one of the great things about this technique is that it doesn't matter whether or not the asteroid is made of a pillow-like material or if it's made like a rock-like material, because you're not actually contacting the asteroid in any way. All you're doing is using the gravity of the spacecraft to move it. So should you be worried? I think the answer is no. Okay? Because you got people like me worrying about it. But you should be careful. Asteroids are our friends. They created the Earth. Now this is a whole talk in itself, why I say this, but believe me, the Earth is made out of asteroids. The asteroids and comets delivered waters and minerals to the surface of the Earth. The water that's in our oceans, the water that you drink, the water that's in your bodies, came from comets and asteroids. You are made of asteroids and comets. Because what, 75% of your body or more is made out of water. So you are made of asteroids and comets. They brought organic chemicals to the surface of the Earth. The building blocks of DNA were brought to the Earth by these objects. And last but not least, they killed the dinosaurs. Right? If it wasn't for the fact that the asteroids wiped out the dinosaurs 65 million years ago, we would not be here. Okay? It's only because they wiped out the dinosaurs for us that we're standing right here talking about this right now. However, they are probably the least likely natural disaster. We all hear about comets. We all hear about hurricanes, tornadoes, tsunamis, fires on a regular basis, sadly, but on a regular basis. So they're very unlikely to happen. But of all the natural disasters, they are the only one which can be predicted and avoided. We can predict it 30 years in advance to the minute when it's going to strike the Earth. And if we know it's going to strike the Earth, we can deflect it so it's not going to hit the Earth. You cannot do that with any other natural disaster. So how do we reduce the risk? We reduce it with a project like the one I'm working on here at the University of Hawaii, called the Pan-STARRS project. We have, we're the main leaders of the project, the University of Hawaii Institute for Astronomy. We got the money from the Defense Department to do this. We have a bunch of partners, including the Air Force, Science Applications International Corporation, and Lincoln Laboratory, and a whole bunch of other partners now. Actually, I haven't even updated the slide. And since our money comes from the Defense Department, I guarantee you we have support from the very highest ranks in the government. Now, this is, Pan-STARRS is a very complicated project. It's going to be a total of about $16 million. I think Phil mentioned that in the beginning. I don't want you to look at this in any detail, but just so that you don't think you're really getting a big treat here, I want to point out to you that I'm not even on this organization chart. Okay? And it's not because I wasn't on the project at the time. It's because I go down here on this project chart. Pan-STARRS is going to be this really amazing telescope system. It's going to be 4 relatively small telescopes. Each of these is a telescope. Down here in the bottom you see a mirror. Each of these mirrors is about 2 yards in diameter, which by modern day professional standards is actually a relatively modest scale telescope. Each of these telescopes is going to have a camera on it that's going to have about 1.25–1.5 billion pixels. Right? So when you think about your little digital cameras, you're talking about maybe 5 million pixels. We're talking 1.5 billion pixels. Okay? It's a huge, huge camera. Each of these cameras is 4 times larger than the next biggest camera in the world, which is also on Mauna Kea, the Canada-France-Hawaii telescope. This is an amazing system that we've been building here. When it starts working, as Phil said, we're going to find more asteroids and comets in 1 month than have been found in the last 200 years. So Pan-STARRS is headquartered here at the Institute for Astronomy, actually off the street of the Manoa Information Center. So you are here. Pan-STARRS 1, as Phil mentioned, is being built on Haleakala right now. It will be operational, we hope, within a few months, where we're going to begin scanning the skies late this year. And then, with some luck and persuading of the government officials, we will get permitting to build the Pan-STARRS 4 telescope system on Mauna Kea and have it operational by 2011 or 2012. Now I want to give you a little bit of idea of what the system actually looks like, because this is not just flying this pie in the sky observatory. This is a real observatory that's currently working. It's taking images of the sky. There are people observing right now, looking at the sky. This is what it looks like, and if you go up to Haleakala, you can take a look at it yourself. We actually have things that move on the telescope, where, like I said, we're taking images. This is the back side of the camera. This would be the cooling mechanism for the camera. Astronomical telescopes have to be, astronomical cameras have to be kept very cold to operate. You can see the dome moving around and the telescope inside of the dome as the sun sets. So the mirror itself is down here inside the observatory. This is the secondary mirror. We're moving things around here. It's a very beautiful, tight little telescope. This is the camera again. I think pretty soon we're going to see a much better view inside the camera. Lots of pretty lights to make it look really fancy. This is the camera itself. This is the 1.5 billion pixel camera. To give you an idea of scale, it's about this big in diameter. It's larger than a chessboard. And with this particular camera, we're going to be able to image the entire sky. And we're going to be able to look at the entire sky every 4 nights. And with this telescope, now you got to wait for this. You're going to see the dawn of a new age of solar system exploration. So what can you do? I'm telling you what I'm doing, okay? What can you do about it? Oh, you got opportunities. I'm only half joking, okay? You can make tax-deductible donations, and we really do need money. So if you do know anybody who can help out, we'd love to hear from you. But let's think about this. How much money is currently being spent on this project and others like it around the world? The 2 movies, Deep Impact and Armageddon, came out at the same time, within the same year. Those 2 movies in 1 year grossed $340 million, a third of $1 billion. Okay, the Near Earth Object Program Office at NASA, which funds projects like mine that try and search the skies to actually stop things like what they show in Deep Impact and Armageddon, has funding of $5 million a year. Okay? So this gives you an idea of the scale of, again, entertainment and science. Now, fortunately for me, if we had to fund my project out of NASA, we wouldn't do it because there's just not enough money there. And that's why we had to go to the Defense Department to actually get us the kind of $60 million that we needed to develop our project. So we need to be thinking a little bit more. When you think about 1 in 1,000 chance of a major impact this century, you might think that $5 million is not really a lot of money to be spending on protecting our planet. So my idea to raise money is to introduce this new University of Hawaii Pan-STARRS credit card. And just like you've got your Discover credit card, or some of the money gets kicked back to whatever organization you want. So I'm suggesting we kick back some of your spending to Pan-STARRS, because Pan-STARRS does a lot of great things for Hawaii and the university. The project itself is 4 years worth of salary for 40 scientists and engineers, and we're building 2 new observatories. That's about $60 million. But astronomy in Hawaii, as Phil was telling you about, is much more than just Pan-STARRS. 10 years of operations of funding for Pan-STARRS is going to be about another $20 million, and this is injected into the Hawaiian economy. This is federal money that gets injected into our state economy, right? So it's people that are spending money at grocery stores and your computer companies and whatever you do. We have Mauna Kea Operations itself, beyond Pan-STARRS and the University of Hawaii. Mauna Kea Operations is a $150 million a year operation that provides over 500 jobs in the state. And of course, tourism. Astronomy, I think, is the second or third leading draw for tourism in the state. That brings in about $10 million a year. There's something like 30,000 visitors a year to the summit of Mauna Kea. So it's dramatic. And of course, protecting the Earth from destruction. Christ. Thanks very much.